Hello and welcome to this first lecture on emergent properties in this course Systems Thinking. So in this new section, we will give you an in-depth view of emergent properties uh, in systems thinking. And in this particular lecture, beginning, we will start talking about how can systems exhibit emergent properties. The emergent properties are those properties that arise from the interaction of systems components but cannot be explained by examining those components in isolation. So let's look at emergent properties. So the systems exhibit emergent properties, as we were saying, when interaction between the systems component gives rise to new behaviors, patterns, or properties that cannot be predicted or explained by examining the individual components in isolation. Now, how does that happen? Uh, how do these kind of properties rise in complex systems? There are many mechanisms. So let's take a look at each of the mechanisms in summary here and then go forward in this and couple of remaining lectures. So first thing is nonlinearity. And how does nonlinearity gives rise to emergent properties? We will take a look at in the remaining part of this lecture as well as in the next lecture. So there is nonlinearity, there is synergy, whereas 1 plus 1 gives an output which is more than 2. So two components give rise to more than what individually they can do. Then there is self-organization patterns, things organize on their own. There are feedback loops that we have already talked about, so we will briefly touch on that. Then there are complex interactions that we will look at. What are these complex interactions that give rise to emergent properties? Then there are phase transitions. And then there is hierarchy in the system that gives rise to emergent properties, adaptation and evolution. And the robustness and resilience becomes one of the properties of the system with emergent properties. So let's take a look at the nonlinearity in a lot more detail. So as we had briefly seen earlier in one of the lectures, complex systems often exhibit nonlinear behavior, where the relationship between the inputs and outputs is not proportional or additive, right? And we talked about this in the section on interconnectedness. Now, these nonlinear interaction between components can lead to unexpected emergent properties that arise from collective behavior of the system. And how does that happen? Let's take a look at that. So these nonlinearity can lead to unexpected emergent properties through various mechanisms. Now, what are these mechanisms? Let's take a quick summary and then look into each of these in detail. So first is amplification and damping, amplifying this input or dampening the input. Second is what is called a threshold effect. At a point, we will look at that. The third is bifurcation and chaos. The first three we will look at in this lecture. And in the next lecture, we will talk about self-organization, resonance and synchronization, non-additive effects, and feedback loops. So let's take a look at amplification and damping. So nonlinear interactions can amplify or dampen the effect of individual components. Small change in one component can lead to disproportionate large or small change on other components. So there can be a disproportionality in terms of either being small or large compared to the inputs, the impact of that. So that is amplification and dampening. Now, this results in emerging behavior that cannot be predicted from the individual behavior of the components. The nonlinearity can introduce threshold effects as we would have seen earlier when small changes in input variable results in qualitative change in the system behavior. Crossing a threshold can trigger abrupt transition or phase changes in the system leading to emergent properties that are distinct from the behavior below or above the threshold. The third thing that we need to talk about is bifurcation and chaos, where a small change in system parameters leads to qualitative changes in systems behavior. It's a bit like the threshold points, right? So bifurcation can give rise to complex dynamics such as chaos. So it's a lot more, let's say, severe than simply the previous one that we talked about. So at this point, in bifurcation point, the system exhibits unpredictable and irregular behavior despite being deterministic, and emergent properties in chaotic system arise from the collective interaction of the nonlinear components. Now, these are like we talked earlier, bifurcations are the critical points in the behavior of the nonlinear dynamic system, where a small change in system parameter leads to a qualitative change in the system behavior, not only quantitative but a qualitative change. And how do these bifurcations give rise to complex dynamics such as chaos? And that's where this happens. So let's take a look at how does bifurcation give rise to complex dynamics such as chaos. So bifurcations occur at critical points in the parameter space of that dynamical system, where the stability or nature of the system solutions undergo a qualitative change. A system which is stable starts becoming unstable. Now, these critical points mark the transition from one type of behavior to another as system parameters are weighed around that point. At bifurcation points, a small change in system parameter can lead to qualitative changes in behavior. For example, a system might transition from a stable equilibrium to periodic oscillation, or periodic oscillation to chaotic behavior as the parameters is varied through at bifurcation point. Near bifurcation point, the system may exhibit sensitive dependence on initial condition, where a small change in initial conditions lead to diverging trajectory over time. The sensitivity to initial condition is a hallmark of chaotic behavior and can cause trajectory to diverge exponentially, making long-term predictions practically impossible. Now, chaotic system also exhibit self-similarity, meaning that patterns or structure repeat at different scales. This self-similarity arises from stretching and folding of the trajectory in phase space, leading to complex patterns that resemble themselves at different levels of magnification. Chaotic systems display non-periodic and aperiodic behavior, where trajectories do not settle into stable periodic orbits but instead exhibit irregular and unpredictable motion. Despite being deterministic, chaotic systems appear random and exhibit apparent disorder. Chaotic systems display topological mixing, where trajectories explore the entire phase space, visiting regions densely and exhibiting no apparent order. This mixing property ensures that chaotic systems explore a wide range of states, contributing to their unpredictability and complexity. The F constraints characteristics characterize the universal scaling properties of bifurcation sequence leading to chaos. These constants govern the rate at which bifurcation occurs and the structure of resulting chaotic uh, attractor, providing insights into universal behavior of the chaotic system across different contexts. Chaotic behavior have been observed in various physical, biological, and engineering systems, including weather pattern, turbulent fluid flows, electronic circuits, and population dynamics. These systems exhibit complex and unpredictable behavior despite being governed by deterministic law. So, in summary, bifurcations are critical points in the behavior of the nonlinear dynamical systems that can lead to complex dynamics such as chaos. Through bifurcation, systems can transit from an ordered state to chaotic behavior, exhibiting sensitive dependence on initial conditions, self-similarity, non-periodic motion, topological mixing, and other hallmarks of chaos. So, having looked at these three things, what do we do next? We will look at more elements of non-linearity, starting with self-organization as we go forward in the next lecture. So thank you so much for watching this first lecture on emergent property in systems thinking. I hope you're continuing to learn new things, continuing to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. I'll be happy to answer your question, and also download the PDF file to take a look at anything that you want to.